Okay, so here we are doing this example from class. First of all, when you're reading this problem here, team of scientists studying the number of deer, 2005 is your starting point, so that's year 0, right? So then it says in 2007, so 2 years later, 31, and 2020, which is 15 years later, and 136. So what they've done right there is they've given you 2 points, basically, 2 points on this curve. So they've given you 2 and 31, and they've given you 15 and 136. So look, those are on this type of function. That's an exponential function, and it's growing. So this is exponential growth. Therefore, I expect a b value bigger than 1, and a is probably, you know, it's bigger than 0 because it's starting off with some deer, basically, to get more deer. Okay, so here we go. So use the data to write 2 equations in this format here that would be used to find a and b. Right. So I am going to say that, let's see, part A, part 1. So I would have that 31 equals a times b to the 2. So I'm putting the 2 there, 31 there. Oops, 2 there, 31 here. So then I have 136 equals a times b to the 15th. Okay, so these are my 2 equations involving a and b based on the information given. And then for part 2, it asked me to solve for a and b. All right, so I can use my calculator. So we can do an exponential regression. You know, put these 2 points in our lists or in Desmos in a table and do an exponential regression. But you can also kind of do this a little bit by hand. So this is a system of equations, so I'm going to use substitution. I'm going to solve this for a right here. So that first equation would be a equals 31 over b squared. So once I have that, I can plug this for a right there because these equations are working together. So I'd get 136 equals 31 over b squared times b to the 15th. Right, I'm just plugging that in. So this makes b to the 13th, so 31 b to the 13th equals 136. So I have to solve for b, right? So I'm going to divide the 31 equals b to the 13th. So now I have to take the 13th root of this problem. So if I'm going to do the 13th root, the easiest thing to do is type in a 13, press the math button, and then go down to this special root there. So that gives the 13 up there. So 13th root of 136 divided by 31. Okay, so that's 1.12 if you round it off to 3 decimal places. All right, once I know that b is 1.12, I'm going to plug it into here. So a is 31 over 1.12 squared. So 31 divided by 1.12 squared. All right, so 24.713. All right, so this is my equation for d of t, right? So d of t is 24.713, and then I got 1.12 to the t. So there's my equation. All right, so for part B is asking to use the data to find the average rate of change. So this 2 and 15, those are the ones they gave me earlier, right? So the average rate of change is going to be the 136. So I'm going to write it a little bit differently first, just so we can see something. It's basically going to be the y values, so d of 15 minus d of 2, all right? And on the bottom, we'll be doing 15 minus 2, okay? All right, so all these numbers I know. So d of 15 is 136, minus d of 2 is 31, over 15 minus 2, that's 13, so that's 105 over 13, so 105 over 13 is 8.077. Right, so it's that many deer per year. All right, so we won't put a label on it. My average rate of change is changing by 8 deer a year, right? Like it's going up by 8 deer every year. So part 2 says, use the average rate of change that we just found to figure out what would be the approximate value at 19, okay? So the approximate for 19, so let's see, so part 2 right here. So I'm going to use the same idea. My average rate of change I now know is 8.077. equals, and I'm going to take over here, so we're trying to get 19, right? So I'm going to put 19, I'm going to keep the 2, and I want d of 19 and minus d of 2. So I know everything in this problem except for that, so I'll solve for that. So d of 2 is 31, so I have d of 19 minus 31 over, this is 17, 8.077. So look, I'm going to multiply by 17, I'm going to add 31, and I'll get my answer for d of 19. So 8.077 times 17 plus 31. So 168.309. 168.309. So basically 168 deer, right? Okay, for part 3 here. So in part 3, we have to kind of imagine what we've been doing. Somebody gave me, I have an exponential growth problem. They gave me 2 points, right? They gave me the points for 2 and for 15, right? And they made me do a line, like do the slope of the line. That was my average rate of change. Okay, but then they asked me to use this information, to use this slope to estimate what was going on later at 19. So this line right here that I have that I'm using, it's the slope between these 2 points. If you're asking me to use this estimate for something in between these 2 points, then the line is going to be above it because it's concave up right here. But because it's after it, so it's after the point right here, since it's outside the data, it's going to be under. So when you ask me, consider the values that we found the estimate for between 2 and 15. Oh, sorry, we're right here. Oh, we did that, sorry, that was 168. It says, are these estimates less than or greater than the number predicted? Okay, explain your reasoning. Oh, I'm sorry, so okay, sorry, so I wasn't talking about the 19. It was just talking about the numbers in between here. So because our graph is concave up and we are doing a line of the line right here, anything along that line is going to be above the actual value, right? So you'd want to explain that. You'd say, you know, the average rate of change is going to be above a concave up area, and so the answers that we're getting using the average rate of change, using the line, are going to be a little bit higher. We're going to be basically above what the model is most likely doing at that time. Okay, so you want to explain that in part 3. All right, so for letter C is also just like an explanation. It says, for which t value, t equals 8 or t equals 23 years, should the team of scientists have more confidence in when using the model D? Okay, well, I think you probably know that 8, right? 8 is within the data that we were doing this model with. So 8 is going to be the stronger, the one that we have stronger information for, because it's within the range, or within the time frame that we did it, within the t values, the domain. It's within the domain. 23 is like way after, it's way after where we have information for. So 23 would not be a good year to try to estimate the deer with our model right here. And that's it, because it's outside the time frame that we made the model for. So you want to explain that. All right, and that's about it.